Hello, and dear students, and the rest of the learners. Welcome to part 4 of a 37-part series of presentations or tutorials in Computer Structured Programming Unit in C and Pascal. This is section 2 of 4 in Program Development and Design, with attention being on Program Development Life Cycle. My name is MemJM. You can simply call me EMELISWAP. In this tutorial, we are going to look at program development lifecycle, which entails problem recognition, problem identification, program design, program coding, program testing and debugging, program implementation and maintenance, and the program documentation. When we talk about program development lifecycle, or PDLC, we are referring to a set of recommended series of steps that are composed or that are supposed to be followed when developing a program. They are a recommended series of steps that are supposed to be followed when developing a program. They are problem recognition, problem identification, program testing, program coding, program testing and debugging, program implementation and maintenance, and the program documentation. It is important to note that in part 3 of this series, I introduced program development lifecycle and also covered step 1 and 2 in PDLC, which was on problem recognition and the problem definition. Therefore, in this tutorial, I'll focus more on step 3, that is program design, all the way to step 7, which is program documentation. When we talk about program design, we are referring to the actual process of the program's processing or problem-solving logic that is called algorithm, which enables the programmer to come up with the models of the expected program. This algorithm is depicted using various tools such as pseudocode, flowchart, control structures, decision tables, among others that we shall discuss in part 5, part 6, part 15, 16, and 17 in the subsequent tutorials. In addition, remember to revisit part 3, in which we discussed more about program design and also introduced the program development lifecycle. Our focus in this tutorial in relation to program design, which is a continuation of part 3, is to highlight some information that you need to know in relation to the data and data structures and how we write instructions, or in other words, instructions writing. When you talk about data and data structures, it is important for you, my dear students, and the rest of the learners, to note that the efficiency and the clarity of a program always depends heavily on what data structures are used. Data must be organized in a logical and consistent way if it is to be of any use. Data structuring means that we can link individual data items into larger data units that have some further meaning. So, a data structure is an arrangement of data items logically together to give information about an individual. The efficiency of a program is a measure of the amount of resources consumed by the program. The types of data that we normally find in programming, or generally, are number 1, the numeric, and number 2, the non-numeric. When you talk about numeric data, we are simply referring to the data, which essentially consists of numbers that can either be whole numbers or numbers with fractions, that is, integers or real. The integers are whole numbers used to count things and they contain no decimals. For example, 743, 200, 20, 1, 16, 90, 1000, 5000, etc. When we talk about the reals in programming, we are referring to that data which contains a fractional part or a decimal point. And this decimal point can appear between 2 or more digits, as well as containing an exponent. For example, 743.67. Then another example is negative 0.0345. Negative, in this case here, is an exponent. We have positive 200.011 or positive 200.011. And therefore, any number containing such kind of symbol or fractions is referred to as a real number. Numeric constants are simply numbers that does not change during program execution, but it remains the same. Therefore, when you have a value or a figure that does not change throughout the execution of a program, whether it's a whole number or it's a number with a decimal point, we refer to it as a numeric constant. For example, if you are calculating the areas and perimeters of circles, we normally have what we call pi, which is usually 3.14. And that figure or that value does not change. It remains that way throughout the process of execution of the program. Therefore, that becomes a numeric constant. And so it is a constant. A numeric constant is a constant that represents an integer or real number. On the other hand, we have what we call the numeric variables. Numeric variables are the memory locations that are used to store numbers which keeps on changing during program execution. In other words, it is a memory location that will hold numbers, but those numbers do not remain the same throughout the program. For example, you may be prompting the user, or the program may be prompting the user to enter his or her age. And then some calculations or tabulations are done, and the next person is prompted for the age. And therefore, that memory location that will be holding various ages, but one age at a time. Once that age is utilized, another value is entered for age, then we call that a numeric variable. A memory location for holding a number, but that number is not specific. It keeps on changing. It is a variable that stores only numeric data. That's what we call numeric variable. A memory location that stores only numeric data, only numbers, but those numbers are not the same throughout the program. A variable, therefore, is a name that is given to represent a piece of data that can be changed or varied while the program is running. But in my subsequent presentations, my dear students and the rest of the learners, you come to understand that in a real sense, a variable is that memory location that is set aside to be holding various data or various content as the program continues to execute. So the content of that memory location continues to change. That's a variable. But if the content does not keep on changing, the content remains the same, whether it's a number or a text, then that kind of a memory is called a constant. And therefore, we normally say that a constant is a value that never changes throughout the course of running a program. Let's now look at non-numeric data. What is non-numeric data? Non-numeric data is simply the data that is composed of characters, strings, logical values, pointers, and dates. Character strings are sequences of data items of type. Strings may contain any printable character and are stored as codes using ASCII, FCD, and other code systems, but mostly when it comes to dealing with text, we make use of ASCII or FCD code systems. My dear students and the rest of the learners, for you to be able to get an in-depth understanding of how data is represented in the computer using various codes, for example, ASCII or FCD and others, kindly visit EMELISWAP ICT YouTube channel and look for the video by the title Data Representation in Computers. Data Representation in Computers. So character strings are a set of characters or text enclosed in single or double quotation marks. A string constant is a sequence of characters or text that does not change during the running of the program. So if you have a certain piece of text that does not change, it remains the same, but it is used by the program at various points as you run the program. The value remains the same. It remains the same. It does not change, but it is of type character, or it is just some text. Then that sequence of characters or text that does not change during the program or during the running of a program is called a string constant. A string variable is a sequence of characters that stores any kind of text information because its contents keep on changing during the running of the program. In other words, if you have a memory location set aside to hold some text, for example, the name of a person, when the first name is entered, the program does what it wants with that name, then the user is prompted for another name, same name is entered in the same memory location, etc. If a memory location is going to accommodate different types of text, different types of characters, or different names, for example, names of people, the same memory location is being used to hold the name of the first student, name of the second student, name of the third student, etc., but one at a time, then we call that a string variable. A string variable, varying, changing. The content is character, but those characters are changing. The content is a piece of text, but that piece of text is changing during program execution. So the first text will replace the second text will replace the first text. The third text replaces the second text. The fourth text replaces the third text. All of them being accommodated in the same memory, but one at a time. Then that memory location that is able to hold those different kinds of information or text is called a string variable. Let's now look at non-numeric data. These are character strings, logical values, pointers, and dates. I have already said that when we are talking about data, we have two types of data. Data that contains or consists of numbers only, either whole numbers or numbers with fractions, what we call integers or real. And the other category of data that we are about to use is non-numeric data. That means it is data which consists of other characters, text, other symbols, dates, and etc. So any other type of data which is not a whole number, it's not an integer, neither is it a number with a fraction. In other words, neither is it real. Then all that other types of data form what we call the non-numeric data. Non-numeric data. all those form what we call non-numeric data. And a non-numeric data, remember, there's what we call, or they are what we call string constants. They are what we call string variables. Let's now look at writing of instructions. Anytime you write a code or a set of code to solve any kind of a problem, then those set of instructions that you write are executed by a compiler or interpreter to do whatever that you want. And therefore, the program statements are normally the instructions that are executed by the compiler or interpreter to do whatever that you want. And they are of three classes. That is the input statements, the output statements, or processing statements. In other words, whenever you are going to write a source code, whenever you want to write a small program or a big program for solving a certain problem, any text that is going to be found there, any piece of instruction that is going to be found within that source code or within that program will either fit as an input statement instruction, an output statement instruction, or a processing statement. It will either fit as input statement, output statement, or processing statement. So a program, most of the programs, majority of the programs that are written by programmers will consist of the three classifications of instructions: the input statements, output statements, and the processing statements. Because some statements or some instructions will prompt you to enter something. Those are input statements. Others will give out the results or they will display the instructions of what you should do. Those are output statements. Others will carry out some computations or some conversions within the processor. And those ones form what we call the processing statements. And therefore, program statements are those instructions that are executed by the compiler or interpreter. Like I have said, they are either input statements, output statements, or processing statements. I'm repeating this section, my dear students and the rest of the learners, so that you can have a general overview of what to expect as we commence the process of writing various instructions, or as we commence the process of writing programs or coding programs. So what are input statements? These are instructions used for reading or accepting data that is entered into the computer by the user from the screen or from a file and store the value in the location with the given variable names. In other words, these are statements that will prompt you to enter something. For example, enter student's first name. That statement which will read that name which you are going to enter is an input statement. So if, for example, you have a statement like enter student's name, that is an output statement telling the user what is expected. But then there's a statement that is going to be coded which will read that name, like read student name, read student age, read age, read name, read. That statement which is picking what has been entered by the user and stores that value in a memory location. That's what we call an input statement. Kindly don't confuse between the two. Don't confuse between input statements and output statements. The input statements purely deal with reading, accepting a value. But those statements will tell you what to do, or they display something. Those are called output statements, as you are going to see. And therefore, the output statements are the instructions that are used to display data that is in the computer's memory on the screen, or writing it to a file. And I have said, those statements also that make the program interactive, those which are displayed on the screen from the program, can also sometimes be referred to as output statements. But mostly, purely, we use the word output statement, or we use the term output statement to refer to those instructions within the source code whose main purpose is to pick some value from memory and display it on the screen, or pick some value from memory and write it in a file. So you can output string variables and numeric variables. The third kind of instructions or statements that we have within a program are what we call processing statements. These are the instructions or statements that manipulate the input data. They involve calculations that are mathematical operations, repeating instructions, selecting instructions, and comparison instructions. Let's now look at the next step, which is program coding. Program coding is the actual process of writing the instructions using a particular programming language, develop a source program that can be translated into machine readable form for the computer to execute and solve the target problem. So it involves typing the instructions into a program editor window into the computer in order to tell it how to solve the problem, and a certain programming language is used. In other words, in program coding, this is the step where you write the source code. This is where you obey the syntax of a certain language, for example, Pascal or C, write your instructions, write your program. So that the process of writing instructions from the first one to the last one using a certain programming language is what we call program coding. The programmers use the program specification and design to write the code necessary to fulfill all the requirements of the program. In other words, before you start writing a program that you want to execute using the computer, you need to take your program through a certain number of steps. Number one, you need to know the problem you are going to solve. Secondly, you need to analyze that problem. Thirdly, you design it. Designing, I've already said, is developing the algorithm, coming up with a set of steps that you are going to follow for the problem to be solved. Developing an algorithm. So in program coding, you now interpret the algorithm by writing instructions using a certain language. So the code is a text-based file, which when compiled, creates the program. A good programmer should consider the following. So if you want to be a good programmer in C or Pascal, you should consider the following. Number one, when you are writing your code, ensure that you write it in a way that it can be modified in the future. So cater for future maintenance. Secondly, write it in a way that can enable programmers to identify the various parts of your code and what those parts do for that code readability. Number three, ensure that as you write your code, it has no defects. And if such defects arise, then there's a way of eliminating them. That is debugging. So bugs can arise from errors in the logic of the program specification or errors in the programming code created by the program. Special programming tools assist the programmer in finding and correcting bugs. Converting the algorithm to the programming language requires the use of specific syntax of that programming language. In other words, when you choose to use, for example, C, you must adhere to the rules of writing source code using C. If you choose Pascal, Pascal has its own grammar. It has its own set of rules that should be obeyed when you are writing instructions, if those instructions have to be understood by the processor. And therefore, we call that syntax. So in converting the design to a program, there are a number of general points and techniques that are important and are applicable to any programming language that you might use. These are, number one, is following the coding standards of that language to write a program. Number two is ensuring that the program written is readable. And number three is selecting a program generator to use in creating reports from the program. Now, every programming language has its own coding standards. And generally, in programming, there are certain standards that we need to adhere to when coding. So standards in the programming aid communication between people working on the same project and increase the interchangeability of people of different aptitudes, abilities, and experiences within and between different projects. So it's always good to code a program in such a way that one can easily tell what each part is doing, even if he or she is not the one who coded it. So a readable program is a program that can be easily understood by the users, by other programmers. The readability of a program is therefore more important than the intricacies of the code. A readable program has the following characteristics. And my dear students and the rest of the learners, anytime you are writing a program, anytime you are coding, ensure that your program contains the following characteristics, because that is what will make it be readable. Number one, it should have meaningful names. Use names that once one looks at them, he or she can tell what they are all about. For example, cost_price, cost price, VAT, selling price. Some rules for creating meaningful data names. Whenever you are developing or writing some names, we call them variables or identifiers. Anytime you are writing them, and I'll expound later the difference between variables, identifiers, and the rest, and how we write them. So some of the rules when you are creating data names are, number one, use names that describe the purpose of the code or variable. Secondly, don't make up aliases. Don't use AKA, AKX, AKA1W. Nobody knows what those are all about. Don't use names that are similar. Change at least 2 letters. In other words, if, for example, you are dealing with students and they're using the name student, and you know you are going to refer to different students, then you can have a name like student 1, student 2, student 3. So at the end of that name, student, you can add 1, 2, 3, etc. to differentiate between them. Keep spellings as normal as possible. E.g., student name, student_name instead of st name. Because when somebody reads student name, student_name, another one reads st name, the one who has read student name will have a very clear understanding of what that is. But if you write st name, that may not be very clear. It may not even be understandable. St can be anything. St can even be anything. Use the same prefix for all variables in one record or the local variables in a subroutine or a module. I will explain more about subroutines in my subsequent presentations. Number two, your program should have comments. These are statements that are inserted in a program code to make the program code more understandable. Comments should be added at the module level to explain the purpose of the module, and within the code to explain complicated algorithms or highlighting error-prone sections of the program. It is good to include these non-executable statements within the code so that anyone reading that program is able to understand its purpose and is also able to understand that program even later, including the person who has written it. And therefore, my dear students and the rest of the learners, it's always good to add comments within the various sections of your program. And I'm going to demonstrate how we add comments in Pascal and in C in my subsequent parts in this series. Number three is indentation. A good program, a readable program has indentation. This is arranging lines of code in a program in such a way that one can easily reflect or see the logic structure of the code. It is advisable to place only one instruction on each line and make sensible use of blank lines and new pages to keep the code readable and limit the components to a manageable size. Number four, ensure that your program has no tricks. Ensure that it is written using straightforward code which people can readily understand. In addition, you should ensure that your program is split up into portions in order to make it easy to understand, especially if it's a large program. That is modularization. This reduces the effort that is required later in the case you want to change or you want to make any changes that the program, or in the case any functionality changes, or if a new feature is added. And therefore, in that case, what we just need to do is to add a new module. So modularization is important. Splitting up a program, make it easier to understand is key. A good program, therefore, has the following characteristics. Number one, a good program is supposed to do what it's supposed to do and meet the criteria that is laid down in its specification. In other words, it should be accurate. Secondly, a good program is supposed to do what it's supposed to do without failing, without crashing. It should be reliable. Number three, a good program is one which is able to make use of the available memory space in a way that the speed of that system is not wasted or is not interfered with. That is called efficiency. Also, a good program should be able to cope with any invalid data that is entered by the user without creating errors or stopping the program from execution without indicating the reason as to why. That is called robustness. In addition, a good program should be easy to use and should be well documented. That is called usability. Also, a good program should be easy to amend. It should have good structure and documentation. That is called maintainability. Let's now look at the fifth step, which is program testing and debugging. This is finding out whether the program content is working correctly and verifying errors if detected. Debugging is the process of finding out any errors or bugs within your program and rectifying them. Therefore, a bug is an error in a program that may interfere in its operation. Program testing involves creating test data designed to produce predictable output. The three types of errors that can be encountered while testing a program are the syntax errors, semantic or logical errors, and runtime errors. When we talk about syntax errors, it's always good to remember, we said in my previous parts that syntax is the structure of a sentence and the grammatical rules governing the structure. And therefore, a syntax error is an error in the grammar of the programming language. This is in terms of spelling, punctuation, naming of variables, and other conventions that must be obeyed by the programmer who are using a certain programming language. These errors are detected by the translator and must be corrected before the program runs. When we talk about semantic or logical errors, we are referring to those errors in reasoning, such as incorrect sequencing of instructions, using wrong symbols, and flawed comparisons, as well as using wrong selection statements, which makes the program not to function as expected by producing incorrect results or causing the program to be aborted during program execution. The logical errors normally don't stop the execution of our program, but the results that are produced may be inaccurate. And this can only be noticed and corrected by the user himself or herself. This is because if, for example, you use an addition sign where you're supposed to use a subtraction sign, then the translator may not be able to detect that. So it is you who is going to detect that the answer is wrong. If, for example, you use subtraction sign where you're supposed to multiply, it is you who will see and know that the result you are getting is not the correct one. Therefore, a logical error can lead to any one of the following conditions or situations. One, the program will produce wrong results, but it will finish normally, or there will be an unusual condition being encountered that may lead to the premature end of the program. When we talk about runtime errors, these are the errors that occur after the program has been tested and debugged, and they occur during the execution or running of the program. For example, the program may get stuck in an infinite loop. These errors also can stop the program from continuing execution because of wrong type of data being entered. For example, where the user is supposed to key in a value, he or she may key in a character or a symbol, and that may make the program to malfunction. So once an algorithm or a program is developed or written, the next stage should be to check that the algorithm or the program is doing what it was designed to do and is doing so correctly. The two main types of testing that you can carry out are manual, or what we call dry running or desk checking, and computer testing. Computer testing includes using translator system. Number two is running program with the test data. Number three is using diagnostic procedures. And number four is doing what we call system test with actual data. The following are therefore the stages and methods used in testing the data. Number one is desk checking. It is also called tracing, manual testing, or dry run. This is a technique of going through your program while it is still on paper for entering it in the program editor so as to detect any obvious syntax or logic errors in the program. My dear students and the rest of the learners, don't make it a habit to be running into using the computer to code your program from scratch. Make it a habit of writing your program on a piece of paper. And then you go through that program, see whether it has any errors. Trace even its results. What do you expect to see when you edit that program or when you code that program using a programming language and the results that you expect to get? So always begin. Good programming methods or principles require that you always write your code in a piece of paper or in a document first manually. Then go through it manually, do what we call manual testing or dry running. And then once you're convinced that everything is okay, then move on and write your program using a programming editor or a program editor. That is a programming language. And that will help you not be able to identify more errors in case they will be there. Tracing involves executing the program manually by using input values or variables and recording what takes place after each instruction is executed. A trace table is a table completed upon manual execution of an algorithm to determine what the program is doing. The first action when creating a trace table is to write down all the variables found in an algorithm as headings, as well as heading output to represent what is printed. If you code a simple C program, for example, like scanf %d, comma, ampersand sign A, ampersand sign B, semicolon. In other words, let me just for now mention what this statement means. If, for example, you are writing a program in C, and this program looks like this. You have a statement which reads scanf %d, the way it is, simply what this statement means is that this program or this statement tells C that, or it requests the user to enter a certain two figures. And therefore, this statement is reading two values. Two values which are whole numbers. Two values which are whole numbers. So the % here, we call this identifier. An identifier for integers, whole numbers in C. Even this other one is an identifier for an integer, a whole number. So simply, this program or this statement is requesting the user, as requested the user. Or let me put it this way. This program or this statement is reading. Scanf is a function for reading. Is reading two values. One value is to be stored in a memory location called A. The next value is to be stored in a memory location called B. So it is reading two values, value A and value B. The content for value A, the content to be stored in the memory called A is supposed to be a whole number. This is an identifier for integer. The second value to be stored in memory location B, which I'm calling value B, is supposed to be a whole number, an integer. So this statement is prompting or is reading. This statement is reading two values, value A and value B. Value A of type integer, value B of type integer. The value A or the value entered for A is stored in memory location called A. The value entered for B will be stored in memory location called B. At these memory locations hold the data of type integer. So this blue goes with this. This other color here goes with this. So what is entered for B? The second value is type integer. First value A is type integer. I'll be explaining more about how we did these kind of statements in my subsequent presentations. Let's now move on. Next, while A is less than 30, this statement means that if the value entered for A is less than 30, then pick what is in the memory location called the A, add to what is in memory location called the B, and then store the results in memory location called B. Pick what has been entered as value A, and to what has been entered in memory location called B. The answer, the results, store them in memory location called B. Then, next, you have the next statement, which is primitive percentage D, comma B. In other words, this statement reads that the processor should display on the screen the current content of the memory location called B, which is of type integer. So display the whole number, the value in form of a whole number that has been stored in memory location called B. That has been stored in memory location called B. Then, whatever is in memory location called the A, add the 4 to it. In other words, get the 4, add to what is in memory location called the A, and store the results to the memory location called the A. In other words, replace the current content of memory location called the A with the sum of 4 plus what was currently in that memory A. So get figure 4, add to memory location called the A, or add to the value in the memory location called the A, and then the result, write them in memory location called the A. In other words, replace what was there with the current sum. And then you end the program, and this continues. This will be continuing until A is greater than 30. I will explain more on the same and the presentations on control structures. So for now, my dear students and my dear listeners, or the rest of the learners, don't worry about that. This section, I have brought it forward for the sake of explaining to you how you do the tracing. So assuming that the user enters or inputs 20 for variable A and 5 for variable B, then our trace table as follows. So in round 1, the user has entered value 20 for A and B and value 5 for B. Then process is 20 less than 30. Remember the condition is while A is less than 30. So is 20 less than 30? Yes. If A is less than 30, then get the value that was stored in A, add it to 5. then assign the resource to memory location called B, and display the resource of memory location called B. Then pick 4 and the current content of memory location called A, that is 4 and 20. You get 24. Replace A now with the 24. So the current value of A becomes 24. Then the program repeats. So is the current value of A is 24 less than 30? If yes, then get the current value of A, which is 24, and to the current value of B, which is 25. That one will give you 49. So display 49. Then get 4 and to the current content of memory location called A, that is and 24. That gives 28. Next route is 28. Is the current value of memory location called A less than 30? So is 28 less than 30? Yes. If yes, get the current value of memory location called A, that is 28, and to 49, the current value of memory location called B, you get 77. So display 77. So is now, or next step is pick 4 and to the current value of memory location called A. That gives 4 plus 28, that is 32. That 32 is stored in the memory location called A. So is the current value of memory location called A less than 30? In other words, is 32 less than 30? No. The program stops. So this is a table that you draw on a piece of paper to trace your program. And remember, my program is the one which I have already displayed here on the screen, which prompts the user to enter 2 values, one for B, the other one for A. Then check whether the value entered for A is less than 30. If it is, then get the current value of A and to the value of B, the resource and in B. Display the resource of B. Then pick 4 and the current value of memory A. Assign the resource in A. Then repeat, check again whether the current value of A is less than that. Proceed again. Get what is in A and to B. The resource assigned to B. Then display the resource of B. Then get the 4 and the current content of memory location called A. Assign the resource in A. Get new value for A. Is the current value of A less than 30? So that will continue until when the condition while A is less than 30 is not met. That is until A becomes bigger than 30. And that's what this table is supposed to do. So that's what we're supposed to do manually. That is called desk checking on dry run. The other method of testing or checking errors is what we call translator system checking, attempt at translation. The translator is used to detect any syntax errors. The programmer corrects these errors and resubmits the program until an error-free listing is obtained. The program is thus run through a computer using a translator program. Number 3 is program run with the test data, just testing sample data. This is carrying out trial runs of the new program using various data variations and extremes of even data with the errors so as to test whether the system will grind to a health or it will inform the user about the anomaly and request for the entry of the correct data. In other words, here you test your program using various types of data, including data that is wrong. See what happens. Test data is also used to verify that the program is doing what it was supposed to do. The program should be tested using suitable test data. If you test using only meaningful data within a well-defined range, you will be assuming that only valid data will be used in the program. It is therefore good to test it even with data that is extreme, that is offside. The data used must be chosen to deal with all eventualities that portray real-world situations and should include extreme data, that is data outside the range, as well as data within the range. And good program should not crash due to incorrect data entry, but should inform the user about the anomaly and request for the entry of the correct data. So the 3 general categories of test data are what we call the normal data. This includes the most general data for which the program was designed. And number two, actual data is used to check for the actual results. So the second category are the extreme values. This tests the behavior of the program when valid data that is either too high, upper limit, or very small is entered. Number three, or the third category is exceptional data. This is entering illegal data that is not within the range or a class of inputs in order to see if the program is capable of rejecting it, rather than attempting to process it to avoid getting wrong results. A test table can be used if a programmer's tool for testing the algorithm, or what we call a test table, is a programmer's tool for testing the algorithm, as well as the code of program for logical correctness. Generally, this table consists of two main columns, one for the input and the other one for the outputs. The programmer writes various possible inputs and calculates the corresponding outputs. When testing the algorithm, the programmer follows the logic of the algorithm in order to check if it gives the appropriate results according to the test table. One input or one important quality of the test table that you use is that it should be one that enables you to select the inputs that test all the different possibilities of the program. These include entries of all the categories of test data, as we have seen. For example, if we write a program that issues students with the comments for pass, if a student has a mean of 50 to 100, or fail, if a student has a mean between 0 and 49, then we will develop the following test table, which we can use to check whether our program would display the same outputs when it's executed by the compiler. So this is an example. You have a column for input, a column for output. To test now, mean, comment. If somebody enters less than 1 minus 100, mean cannot be negative. So that should be the output. So one side is some values entered. The other side is what is expected. What is expected. Kindly note, I have negative 100 minus 100, which cannot be a score. So what should happen is that the program should give out comment. Mean cannot be negative. If somebody enters a B, that is an extreme, but that's not a score. Then the output should be mean can't be alphabet or a special character. So these are situations that we need to check. You enter, assuming somebody enters a B, what should happen? Should the program crash or should give out some comments? That's the purpose of this test table. If somebody enters over 100, that's 101. That's the extent, that's beyond. So the message can be mean can't be more than 100. So we call this a test table. You use it, test your program. Whatever value is entered, let there be respective output. Using the fourth method of debugging or rectifying errors is using, or identifying errors, is using debugging utilities or diagnostic procedures. This is running diagnostic procedures such as trace routines during translation to detect syntax or logical errors in order to correct them for execution. A trace prints out the results at each processing step to enable errors to be detected. If a trace is not available, the programmer can insert instructions in the program to print out immediate results at the key points. The fifth method is doing what we call system test with actual data. That is testing by users. As part of the acceptable trials, new programs are usually run in parallel with the existing system for a short time so that results can be compared and adjustments made. The system test is made using actual data, the actual environment. The sixth step is program implementation and maintenance. Implementation is the actual delivery and installation of the new program ready for use and training the users for the system design. Review and maintenance is also important because the errors that may be encountered after the program has been implemented or exposed to extensive use are bound to arise. So it's good to review your program after it has been installed, so that in case it's found that the program is not meeting the original objectives, some corrections or rectifications can be made. Maintenance is ensuring that the current programs are operating error-free, efficiently, and effectively. A program may fail due to improper use, as proper training, past implementation, support of users will reduce chances of having them entering invalid data that crash the program. In maintenance, the programmers update software to correct the errors, improve stability, standardize and adjust to organization's changes. A common practice is to run the new system in parallel with the old system in order to ensure that if something goes wrong, the business does not come to a grinding halt. After a number of successful parallel runs, then the old system is abandoned and the new system will become fully operational. At this point, the system goes into the final stage of monitoring, review, or evaluation, where the performance of the system is evaluated with reference to initial requirements. After a new program has been implemented and has been in use for some time, a new need may arise due to a new problem, a new directive or a new opportunity which may still make the analyst discover a need for a new system or modification, or have complete overhaul of the entire program. And therefore, this invokes the restart of the program development life cycle, because you have to begin the problem recognition, the new problem that has arisen, understand it, define it, design it, code it, debug it, test it, implement it, and maintain. The last step, which is not usually a step per se, is documentation. This is the writing of support materials explaining how the program can be used by users, installed by operators, or modified by operators. Documentation is a document showing what the program does and it can work under what conditions. It is written, or it is a written explanation of how the program works. My dear students and the rest of the learners, kindly note that it's good to do documentation at each and every stage. Not to do documentation just as the last step. Every stage should be documented. So in as much as possible, always ensure that you do your documentation from the beginning of problem recognition all the way to its maintenance. So once you are through, then you can do what we call final documentation, where you do the final touches on various aspects of the program. But don't just wait to document or to do the write-up after you have with all the stages. It's always good to do documentation of each and every stage. Remember, you have seen there's even internal documentation where you do the indentation, you add the comments and etc. And there is also documentation of the installation of the program and how to do various errors. And therefore, it's important to note that all the stages of a program development should be documented in order to help during future modifications of the program. For that reason, program development is, or program documentation is not usually a stage or a phase by itself, in as much as it is treated to be the last phase, because it's supposed to be done at each and every stage or phase in the program development life cycle. Documentation is therefore an integral part of the inspection process. It ensures that the intentions of the originator of the system survive from specification to design and from design to coding. We shall discuss more about program documentation in part 7 of this series of tutorials. That is, I'll speak much about documentation